Hello and welcome to another walkthrough. This time will be the pure mathematics for the year 13 students in the UK, and this is paper from 2024, the most recent one as of the time of recording. For full transparency, I've kind of like half done the paper but didn't check the mark scheme yet. Okay, so this time I'm not going to be timing myself. I'm just going to walk through all of the questions in one video and I'm going to tell you my thought process along the way. Let's get on with it. First question. Okay, so this function gx is a polynomial function, a cubic function, where k is a constant. Given that x minus 3 is a factor of gx, find the value of k. Right. So this is actually kind of easy. Probably one of the questions that you have to nail it and make no silly mistakes. So from the factor theorem, when we are given a linear factor, we can substitute the critical value into the function. So in this case, the critical value is 3, right? Because x minus 3, the critical value is the value such that when you substitute into the x minus 3, it becomes 0. So we're going to sub this into the g of x function. So we are doing g of 3. And then if we substitute into all the x's, we get 3 times 3 to the power of 3 minus 23 to the 2 plus k plus 17 times 3 and then plus k. So I'm just going to move here a little more to the left. Okay. And we also know that from factor theorem, this must be 0 because there's no remainder for the factor. Yeah. And then I'm simplifying this. So 27 times 3 is just 81 minus that's 9 times 20, 180 plus this is 3k plus 51, expanding all out. So I get 4k equals, okay, all the numbers there, we have 132 subtracted by 180, so that's 48, right, is it? Let me just check, double check here, I mean, 132, yeah, 48, so k equals 12, right? Yeah, because we move on the other side. Let me just double check everything again. And of course, after this walkthrough, I'll mark the paper as well because I didn't know the answers yet. All right. Yeah, I think I'm happy with that. So that's the first question done. Number 2. Yeah. Zoom in a little more there. Okay. So number 2, part A, find in ascending powers of x the first 4 terms of the binomial expansion of that. All right. Give each term in the simplest form. So part A, well, this is the binomial expansion where you have to make the first term become 1, right? Because this is where the power might be a fraction or a negative number, right? So we have that formula there, which is n1 plus nx to the power of, 1 plus x to the power of n, right? So we're just going to expand. So the first term will be 1 to the power of n. So it's just 1 to the power of the power, which is n in this case, which is a half. And then we do plus n which is a half, x in this case in the formula would be the second term, which is minus 9x, right? And then the next term would be easy now. Okay, this is the second term, so this is 1 factorial here. And then, yeah, I can just write it like that. So 1 factorial. So this is actually 0 factorial if you wanna complete formula there. And then this is 1/2. You gotta keep subtracting by half. By 1. So you get a minus 1/2 here. And then that becomes a power of 2. And the division here would be by 2 factorial. So if you see the pattern, this formula is very easy to remember. I mean, you don't need to remember it even. Yeah, it will just stick into your head in time. So first 4 term, we are short by another term there. Okay, I'm just going to go and subtract another term here would be minus 3/2 if you keep subtracting. And then this would be 9x to the power of 3 or divided by 3 factorial, right? And that's it. You just simplify all the term. Okay, so the first term, 0 factorial is 1, so 1 to the half is also 1. So 1 plus The second term is minus 9 over 2x, right? Yeah. And then the third term, well, we got a positive number from here and a negative sign from here, so it should be a negative sign. Okay. And then we have over 8, so this is over 4 and this is 2, so it's 1 over 8 here, all this. And then this is 81, so 81 over 8, right? Minus 81 over 8, is that simplifiable? Don't think so. So it's minus 81 over 8, x squared. And the last term, okay, seems like this is 3 times 2, so 3 cancel that. So we have 2, 3 2's here and one more here, so that's 1 over 16 there. 16, this is 3 negatives, 2 negatives, so this is also negative, okay? Over 16 there, and x to the 3. And then what do we have here? We have 9 to the power of 3. Is it simplifiable with the 16? I don't think so, because 16 is 2 to the 4, but this is basically all of the 3 is there. So 9 to the 3 is, I believe, 729. Okay, so that's 729. Yeah, I think that's fine. And it's a negative term. Okay, so I think I'm done with this one. That's part A. Part B, give a reason why x equals minus 2 over 9 should not be used in the expansion to find an approximation to root 3. Okay, so there is a very condition that you need to know, right? Because you are required to know this. That when you have the usual n plus x to the power of n binomial expansion here, the infinite expansion, it's only valid when the modulus of x is less than 1. That is just saying that this term should be small, because when you keep expanding, okay, this is the concept here. If you didn't know it, then you should know. When you keep expanding, right, as you can see, you will have increasing power of x. And if the x, or the second term here in the form, if it's greater than 1, then the term gets bigger and bigger. Now, what's wrong with that? Well, there is something called convergence. If the consecutive terms get bigger and bigger, that expansion will not be a good approximation for anything. Because how can you use it to approximate anything if it gets bigger and bigger for the, for the other terms, like the consecutive terms, right? So as you've already seen and experienced, usually we only expand up to the third or the fourth term, because that is already a good enough approximation, because we can cut the higher order x term because they are getting smaller and smaller. So they are getting smaller and smaller only because the second term here is smaller than 1. For example, if it's 0.9, you keep multiplying 0.9, try that in the calculator, you will see that it gets smaller and smaller and smaller every time you do that. And that is the key concept of the validity of this binomial expansion concept. Yeah. Now I have talked too much, so I need to get right back to the question. We are explaining why minus 2 over 9 should not be used. So let's see. If that is the usual concept, but we actually have 1 minus 9x to the power of half, right? So we should say that, well, okay, the minus 9x modulus should be less than 1. Well, that is to say, right, that this whole thing, yeah, is less than 1 over 9 if you divide by 9 on either side, and it should be in the range. If you have done modulus, then it should be the range of this. Now, minus 2 over 9 is out of the range, right? So this whole thing only valid for that, right? So that means minus 2 over 9 is not in that valid range, okay? Not in the valid range of x, so it should not be used. Okay, that's it. That's the concept there. Because if it is minus 2 over 9 and you actually do use it in the expansion, you know, the terms will get bigger and bigger in the size, in magnitude, which doesn't make this binomial expansion good anymore. All right. Okay. Number 3. Okay. Okay, so number 3, fx equals x plus tan half x, and there you get the domain, given that the equation of x equals 0 has a single root alpha. Okay, so show that alpha lies in the interval of that. Okay, so this is classic. We're gonna just sub in 2 values and check the change of sign, right? So that's easy. So I'm just going to do f 3.6 equals and f 3.7 equals. So just for working sake, we're just gonna do that. Yeah, just for the working, yeah, working marks, which I think just one, really, or actually none. Okay, so I'm gonna use a calculator, and let me check in radian mode. So 3.6 plus 10 of 1.8 there, because divide by 2, so I get a minus here. And then if I just clear and do it again, oh sorry, it should be divided by 2 as well. Okay, so 0.211212. Here we go. Well, just out of interest, did I aha, hang on. Wait, no. I just want to check the first one again, just in case. As you can see, I'm quite careful. Okay, there we go. So there is a change of sign of fx while being a continuous function in the range, in the interval 3.6 and 3.7. Therefore, a root alpha lies in between the interval. Okay, that's it. That's typical, and that's how you write. The important thing here, you need to write being continuous function, because there is a exception where it's not continuous, right? If it's not continuous, then there might be where the asymptote lies, and there can be no root in the x-intercept. And that's part A done, right? Part B, find f dash x. So the derivative of fx there. Okay, we're just going to differentiate that. So differentiating x, we get 1. Okay, differentiating 10, we get sec squared. So it's a sec squared, and the angle will be the same, but then we do a chain rule in the inner function, which is the angle right there. So we're going to have to multiply outside by a half. Okay, so that's a chain rule there. So that's done. Like just the working and the answer in one line. Using 3.7 as the first approximation for alpha, apply the Newton-Raphson method once to obtain a second approximation. So the Newton-Raphson method is saying that the xn plus 1 would be equal to xn. Wait, actually I might forget. Is it this? Fx of n and then f prime x of n plus 1. No, n, right? So that's Newton-Raphson, isn't it? Let me just check the algebra here, because n f prime xn, that should be a plus, right? Should be a plus here, I think. Actually, let me check the formula sheet. I forgot to keep my formula sheet with me. Formula sheet, Edexcel, A-level, math. Just to look at that formula right there, guys. Yeah, no, it's a minus actually. Sorry about that. Okay, so this is a minus, and everything else is fine. Okay, I'm gonna keep formula sheet on the right of the screen. You can't see it, but you can keep it open. Okay, so we apply the formula. So the first approximation being 3.7, we just plug 3.7 in here. Fx being f of 3.7, so it's just 3.7, yeah, this whole thing, plus tan of, we actually got it from here, right? If you remember. Yeah, we can make use of that. And then divided by the derivative where you substitute also 3.7 in there. So we are gonna substitute onto this one. Let me shrink the whole thing a little. Okay, so it's 1 plus 1/2 6 squared of 3.7 over 2. I'm just gonna plug everything in the calculator all at once because we only required to just obtain the second approximation and then we're done. Okay, so 3.7 minus fraction 3.7 plus tan of 3.7 over 2, and then down here we have 1 plus 1/2 times sec, which is 1 over cos, right? So that's 1 over cos, so I'm going to do bracket here, and cos 3.7 divided by 2, and then close bracket squared. So that's my sec squared there. And that will be, so we got to give it into 3 decimal places, so I'm just going to do 3.672, my answer. That should be fine. That's close to 3.7, so it converges quite quickly, this method here, which is pretty cool. Okay, so that's the whole number 3 done, guys. Let's go to number 4. Number 4 seems fine. This is to prove from first principle to show that the derivative of x squared is 2x. Well, I think you might have seen a video in YouTube about the proof of this. Is very simple. You can prove it by using a graph, or this is first principle. I also made a video about first principle, so if you haven't checked it out, so just go check it out there. The way to do this is to actually use the first principle formula, and I believe, let me check the formula sheet if there is first principle. Yeah, so if you look at the formula sheet, you should be using this one. F derivative of fx is limit of this function right here, limit of h going to 0 of this very function. So as you can see, like this function is actually finding the gradient of the curve. It's doing delta y there on the top, and the h is just the delta x basically, right? Okay, so we're just going to substitute in, and in this case fx would be x squared, yeah. So that means f of x plus h would be x plus h squared. So that is x squared plus 2 xh plus h squared. All right. So we're going to sub everything in. Limit of h going to 0. And that is just substituting the actual expression in each one. Okay. And h. Now the way to do this is not to substitute h right now. We substitute h when we already simplify the top expression. Okay, so this is limit of h go to 0. So the top one, as you can see, we can cancel the x squared here. Yeah, so we're only left with 2x, 2xh, and h squared. And you can simplify, can you not, the h out, so you get this over h. And again, the h can also cancel there. And it's going to be just 2x plus 0. So when you are left with 2x plus h, you have nothing else to simplify. Then you substitute the h in. So you get 2x as required. Yeah, by first principle. Okay, that's pretty neat. Number 5. The function f is defined by that. Show that the derivative of f is that. Well, this is just simple, probably quotient rule of differentiation there. So we can just start the quotient rule right now. So quotient rule says v du minus u dv over v squared. Yeah. So v being the bottom bit, u being the top bit. Yeah. V. Yeah, this is the v. Du means differentiating u. Differentiating the top bit, you get 2. Minus u, which is the top bit, just write it down. Putting the brackets in would be nice. And differentiating the bottom bit, dv, right? So dv, we have 2x. Okay? You should be familiar with differentiating all these functions. And then the bottom bit squared, which is the v squared. Okay, as you can see, we now get the bottom term to be the same as what is required there. Okay, so we are kind of okay. And if we expand the top bit, we get 2x squared plus 8 from the left part, and minus 2x times 2x is 4x squared. 2x times minus 3 is minus 6x, and plus 6x because you have a negative sign there. Got to be really careful with the sign when you expand things. Yeah, can get things wrong there. Okay, and then we hence have the top bit being a negative. Okay, we're just going to do negative 2x squared plus 6x plus 8. And that is what is required by the question. Yeah. Well, let me double check everything. Yeah, because I can't be careless about this. It's simple. I shouldn't make it wrong. Yeah, and then 4x squared plus 6x. I think I'm fine with everything. Am I not? Yeah. Okay, so that's part A, right? Part B. Hence, using algebra, find the values of x for which f is decreasing. Okay, so important. When f is decreasing, that means the derivative is negative, right? So f prime x should be less than 0 for it to be decreasing. Yeah, and we're going to find the range of this. Okay, so we put the whole thing as a negative. Now, as you can see, this is already a positive. Yeah, so it's like when you put this whole thing less than 0, you can multiply this to cancel it, because we are not considering the bottom part now because it's always positive anyway. So we can only say that the thing that needs to be negative is just the top part, right? Just the top part there. Okay, because something divided by a positive number is less than 0, then you got to get the top part being a negative number. That's why I put the top part less than 0 here. Now, if we simplify by minus 2, we get x squared minus 3x minus 4 greater than 0. I just divide the whole thing by minus 2, and I needed to flip the sign there. And I can factorize this as x minus 4 and x plus 1 greater than 0. Okay, so this is where you have a greater than sign, and from PO1 last year, in year 12, you should be familiar that therefore the range of solution should be x greater than the upper one or less than the lower one. Okay, so that's the range of solutions to x when this function is decreasing. Yeah. Okay, so that's it for this one. Just checking. Yeah, I'm fine with that. Okay, the next one, number 6, right? Number 6. We are given this graph right here. Figure 1 shows a sketch of the graph with equation, a modulus function there. The vertex of the graph is at point P right here, shown in figure 1. Find the coordinates of P. Well, to make this very simple, we know that the vertex is kind of like the minimum, right? So that happens when you, because if you look at the first term here, it can only be minimum at 0, right? If you put the modulus part here being 0, the whole thing becomes 0, and The minimum is at 5. So that is where the y value of this p is 5. That's the minimum, right? And that happens when you make the modulus term 0. Yeah? So to make the modulus term 0, you got to put x as 2. Make sure you follow that if you didn't know how to do this. So it's just the coordinate of p would be 2 and 5. Didn't have to write anything because it's just, wait, hang on, it's 2 marks here. I think that's fine. Well, we can show some working, right, just in case. So I'm just going to do like x minus 2 equals 0, so x equals 2. And then y equals 5, so coordinates of p would be 2, 5 there. That's it, just to explain that. And that's part A. Part B, solve the equation. Right, now I prefer to do this graphically. Well, not getting, what I mean by that is not to get the x and the y value by just looking at the graph and draw the, and use interpolation or extrapolation to get the values from the graph, but we use the graph to get some idea of how to do this. Okay, so I'm just going to draw this one quickly, and that is the function of 3 modulus x minus 2 plus 5. Now you have another expression on the left side of the equation, 16 minus 4x. And 16 minus 4x is actually steeper and is a negative linear function, right? And it's steeper than the modulus part because we just look at the gradient here. So if you expand 3 in, you're going to get 3x. So the 3x here and the minus 3x here will be the gradient of the v shape. Because 3 is smaller than 4, so we can kind of like draw the other line like this. So if you get the y-intercept of this v shape, it's going to be, if you put 0 into the x, you get 11, right? This is 11. But if you draw the other part, it's going to be further up because the other linear equation is 16 minus 4x. So 16 is, say, somewhere here maybe. And it's going to be like this. Or somewhat, close to that. Now, what's the point? As you can see, if you didn't draw the graphs here for the two functions, you will have got two answers. You can try that. Solve it algebraically, but blindly, without being aware of the graphs, will lead to two answers. Usually, it leads to two answers, right? But from the graph, you can see clearly that there is only one intersection between the two functions, right? There is only one intersection there. So, now, how do we get the answer? Well, we're going to have to try well, actually, I'm thinking, let me try, to make sure whether it cuts the left part or the right part of the V shape here, we need to get some idea. So I'm going to do that by just substituting x equals 2 into the linear function, not the V shape, to get some idea there. So this is 16 minus 8, which is 8. So when x equals 2, the orange line will pass 8 on the y-axis. While the V shape, as you already know, this is 2, 5. So actually, I drew it incorrectly. I need to make it more like this. More like this. Yeah, more like that, maybe. Because at x equals 2, the point is further above 5. Right? It's not 5, it's 8. So this is what I was saying, 2, 8 here, when I plug x equals 2. So that is indicating that the orange line cuts the V shape on the right part of on the right wing of the V shape. So that means when we make an equation to solve, we should do the orange equation, the orange line, equals the right part of the V shape. So the right part of the V shape is when you have a positive gradient. So how do you get a positive gradient? Well, if you take out the modulus sign without putting a minus in, because that's how we do to get the other one. You don't put the minus in, you already get a positive gradient from that. So I'm just doing 3x minus 2 plus 5. And if you did want the negative part, then you would have just had to do a negative like that and times 3. Okay, just put one negative in. But this time we want a positive because we know that it will cut there. So we solve the equation basically, just do the algebra here. So I got 7x on the right maybe, and then I move everything to the left. I get 17, so x equals 17 over 7. Just like that. Let me check everything. I can't be too careless about this. So minus 1, 17. Yeah, that would be the answer. So, yeah, already solved it. Okay. Now, a line has an equation y equals kx plus 4. This is another one now. Given that y intersects that equation again, that function again, at two distinct points. Now, this is another one. This is another type where you need to be careful. Okay, I'm going to draw the V shape again, quickly. That's point P there, being 2, 5. Okay, so y equals kx plus 4 seems like it fixated the y-intercept at 4. But we already know that the y-intercept of the V shape is, what was it again? 11, right? Because if you sub x equals 0 in the modulus function, you get 11. So x equals 4 is around here maybe? Well, just below the 5 there. So just make it that. Maybe I should move this down a little further to make it more realistic. Okay. Now, k is an unknown. So we don't really know yet how it's going to look. Is it going to look steep, passing 4, or is it going to look... So I'm talking about whether it's going to look like that or like that. Now, let's do some thought process here. We have to make this line of an unknown gradient cut the V shape at two distinct points. So the critical point beyond which it starts cutting at two distinct points would be the vertex, right? Just at the vertex. Because if you ever so slightly tilt the line a little more, you cut 2 points. But if you have less gradient than this, then like when the gradient, when it cuts exactly at vertex, if you have less gradient, smaller gradient, it doesn't cut at all. So the critical point we need to find this. This is where it's critical. So at critical, yeah, just start cutting maybe more than 1 point. At critical here, cutting 1 point. At critical, the line of an unknown gradient intersects the vertex of the V shape. So x is equal to 2, y is equal to 5. You can just substitute these two coordinates into that linear function of an unknown gradient. So it's just 5 equals k missing, we want to know it, and x being 2, and then 4. So you solve for k like this. Now, I just spotted that we need to find the range of values of k. Well, this is the value of critical k, so we're just going to solve for it. So k being 1/2 here, right? Okay. Now, why does it ask for the range? Well, because of course, if k is 1/2, it's just going to cut the vertex at that. But at this point, it only cuts once, not 2 points. So we need to make k more, right? I mean, if k is greater than 1/2, no matter how greater it is, it's going to still cut at two distinct points. So that's our range, right? That's our range. I'm just going to, yeah. So therefore, k is greater than 1/2. Don't be intrigued when it says values. If you only read values there, you might think, okay, do I need to get another bounds? But there are infinite values that k can take here when we say k greater than 1/2. It can take 10, it can take 10 million, whatever. Still cut 2 points, right? So that's the answer there, yeah? Okay? Not less than that, not equal, because when k is equal 1/2, it only cuts once, not 2 points. That's done. Okay, and then question 7. Figure 2 shows a cylindrical tank of height 1.5 meters. Initially, the tank is full of water. The water starts to leak from the small hole at the point L inside of the tank. While the tank is leaking, the depth h meters of the water in the tank is modeled by the differential equation. right? So this is integration, separation by separation variable, right? But that is specifically the technique to use for the differential equation like this one. Using the model, show that h equals blah blah blah. So basically we need to solve this differential equation, and by that I mean just integrate it. Yeah, so we're going to integrate it, but before doing that we need to separate the variables, hence the technique. So it's just dh equals minus 0.12 e to the power of 0.2 t. Got to write the question here in part A. Yeah, and then we move dt up here. And then when we integrate both sides, we're going to get the answer. We're going to get the what's called the solution to this differential equation, which is just to make h as a subject and then the function of h there. Okay, so this one we just got h, and then this one would be so differentiating an exponential. So we just copy everything and then use a reverse chain rule. So I'm going to divide by minus 0.2 here, and then a plus c, right? Because don't forget we have a plus c as well. So that's very simple. And then we simplify that, we're going to get, that is going to be 0.6, yeah, e to the power of minus 0.2 t plus c. Now we need to find the constant c. So we should have some information here. Water starts to leak from small hole. Let's see. Oh, well, a and b are constants to be found, right? Okay, let's see. Initially, the tank is full of water here. Yeah, you gotta keep reading, right? So initially is the initial condition. So that is when t equals 0. When t equals 0, the height of the water should be 1.5, right? Yeah, because that's full of water initially. So we sub in 1.5 equals 0.6 e to the minus 0 here. So when e to the minus 0, sorry, e to the 0 goes to 1, right? That goes to 1. So we have 0.6, so c equals 1.5 minus 0.6 equals 0.9. That would be the c value, right? So we just, again, sub in everything. So that's the answer there. See if we get the right form, minus 0.2t, a and b. So I'm fine with that. Okay, next one, part B. Part B, find the time taken for the depth of water to decrease to 1.2 meters. Given your answer, okay. So the depth to decrease to 1.2, basically we can just substitute 1.2 into the h here. So 1.2 equals, what was the equation again? 0.6 e to the minus 0.2 t plus 0.9. That's just the equation we got earlier, right? We're going to be using that to solve for the time. And note that the time, t, is in hours, but it asks for hours and minutes to the nearest minute. So we got to be careful with that, right? I mean, every time you think you got an answer, you might not. Because it might be the answer you think the question asked, but the question might not ask the question to that answer, if you know what I mean. It might have a different question, so try to be careful there. That's the bottom line. Okay, anyway, so I'm solving this, so I get 0.3 equals 0.6 e to the minus 2t there. So dividing both sides by 0.6, I get 1 over 2 here equals e to the minus 0.2t. So it's a ln of 1 over 2 here equals minus 0.2t. So t is ln of 1 over 2 divided by minus 0.2. We're just going to use a calculator for that, of course. So ln of 0.5 divided by minus 0.2 surely should be a positive number. Okay. If I multiply this by 60, yeah, multiply this by 60, sorry, like that, it's going to give me the things in minutes, yeah, like that. So this is about 208 minutes, right? Yeah. Just multiply it by 60, not to be confused here, because we got this in hours. We multiply by 60, we get everything in minutes. But then 208 minutes is 3 hours, right? Because 3 hours is 180 minutes. It's 3 hours and 28 minutes. Yeah, that's it. 3 hours and 28 minutes. Yeah, that's it. The time taken. So that should be a period of time, not the time in the clock, because sometimes it can ask the time in the clock given the start time, let's say midday or something. It can ask you the time, not the period of time. So you got to be careful with that. I think I'm happy with that answer. Okay. So next one is part C. All right, see, I'm gonna write there. In the long term, the water level in the tank falls to the same height as the hole. Okay, yeah. Find, according to the model, the height of the hole. Yeah, we don't know yet. It's just this height here. Okay. From the bottom of the tank. Basically, let me just translate that to English. It is asking you the value of h that will be reached when you progress the time indefinitely. So when time progresses indefinitely, like tends to infinity. So when times tend to infinity, that's like a very, very long time. Okay, let's say. What is the value of h that is reaching? Okay, so when t tends to infinity, right? We look at the exponential term. E to the minus 0.2 t will tend to 0. Because when you substitute e to the minus some number, let's say e to the minus 1,000, you can try check that in your calculator. The number will be very small. So this term will go to 0. That means the whole h equation will be equal to, yeah, b. And what is our b? 0.9. So that is the answer. The height from the bottom of the tank of the hole, which is 0.9. And that makes sense if you think about it, because in reality, the water can only leak up to the level of the hole. It can't really keep going down, can it? Because that doesn't make sense. How can you still leak the water out when you are below the hole, right? So that's kind of like what it's saying there. All right. So there you go. Next one, question 8. Okay. The functions f and g are defined by these. Find f of g of 2. Okay, that's fine. Number 8, A. Well, f of g of 2, so g of 2 first then, because it's the inner function. So equal 5 over 2 times 2 minus 9. So that's 5 over minus 5, so that's minus 1. So f of minus 1 is, we substitute minus 1 into the function. That's fine. So minus 1 squared is 1. And then 4 minus 3 is 1. So that means f of g of 2 equals 1. Okay, that's fine. Find g inverse. Okay, this one we got to be careful, right? Because whenever you are asked to find the inverse, I believe that's the inverse. It doesn't have a minus there, but I believe it is. Whenever you are asked to find an inverse of some function, you got to give the domain. Yeah? So we asked to find the g inverse, so I'm just going to do x equals 5 over 2y minus 9. You know, this is just for the working marks. Actually, there is a neat trick to just find the inverse very quickly. But you guys need to work on this, need to write this when you sub x and y, swap them and then rearrange. So I multiply that out by 2y minus 9, so I get 2xy here and minus 9x, right? Equals 5. And then we pull y out, so we make y the subject, so it's going to be 9x plus 5 on the right side, and then divided by 2x here. Yeah, so that's just the inverse then. So g inverse x equals 9x plus 5 divided by 2x. That would be the answer there. Now, I was mentioning, yeah, that when you are asked to find an inverse of some function, you should also give the domain. Okay, now but the domain of G inverse is the range of G. So it is safer, it is more secure if you find the range of G instead, rather than finding the domain of G inverse directly. Because sometimes the limitations of domain, either domain or range, might carry over to the inverse without you realizing it. So, but strictly speaking, the domain of G inverse must be the same as the range of G, because that's the function and domain thing, domain and range property between the inverse and the function. So let's find the range of G. Yeah. Now the range of G will have a limitation depending on the domain of, the range of G will have a limitation depending on its domain. But its domain just can't be 9 over 2, and that is purely because you can't sub 9 over 2 into the denominator here, because otherwise it would go to 0, right? And we can't have division of 0 there. So that means there is no limitation from the domain this time. That means the range of Gx is only limited by its nature. By that I mean, if you have a rational linear function like one of these, like what I'm writing here, if there is no limitation to the domain, like domain can be anything except minus d over c in that form. So here x cannot be minus c over d. If this is the case, yeah, x can take anything but just that value. If this is the case, then y cannot take only one value, which is a over c. So a is the coefficient of x on the top part, c is the coefficient of x on the bottom part. If you look at the original function g there, the top part doesn't have any a. So a is 0 on the top part because you don't have any x term. So a is 0. The bottom part, whatever it is, if you do top divide by bottom, you get 0. So y cannot be only 0 in this case, right? I'm just going to rub that off. So I'm just writing here, because the range of G is such that y cannot be 0. So that means the domain here of G inverse is such that x cannot be 0. And that is kind of evident if you look at the function there, but yeah, it should work like that. But sometimes if you don't look at the original function, you might get it wrong, just from my experience, yeah? Okay, so it's safer to do it like that. Okay, so x not equal 0 there for the domain of G inverse. Ci find g of f of x. So that's a composite function, so we're just gonna maybe move on to the next page here. So g of fx then is going to be subbing g by that thing. Yeah, so I'm just going to sub the whole thing into the g expression. So we sub this whole thing into the function of g there, because fx is the inner function. All right, so we simplify that. Given your answer as simplified fraction. Okay, we're going to try our best to simplify that. So it's 8 minus 6x squared minus 9. So it's it's minus 6x squared minus 1. But if you want simplified, then I can give you like minus 5 divided by x squared plus 1. Sorry, 6x squared plus 1. How about that? Yeah, you can pull the minus out. Okay, so that's it. And then we deduce the range of this guy. So the range of this guy is the range of a composite function. So that's tricky actually. This one might be tricky. The range of a composite function can be determined by, you gotta look at the domain of fx, right? The domain of fx obviously is real number. That means the domain has no limitation. But if you look at the range of fx, so range of f here, yeah, range of f, the range of f can only be the numbers that are less than 4. Because if you look at the function there, 4 minus 3x squared, the fx function, this is a parabola, an inverted parabola, right? And the maximum is 4 there. So the range of f, y less than or equal 4. Now here's the trick. The range of the inner function, this is just the way I do it, yeah? This is just my personal technique. The range of the inner function in a composite function, so we have g of f of x here. Whatever the range is in the inner function will become the domain of the outer function. So we are using the range of f here as the domain of g. Because if you think about it, when you have a normal function fx, whatever you put inside the brackets there will be called the domain, right? That's just a one single function. It's not a composite function. It's just a normal function. Whatever you put inside the brackets will be called domain. So, you put the whole fx inside. Of course, this whole fx will become the domain of g. But what is actually the fx? Well, the values or the ideas you get about fx is to get the range, because that is what fx is. It's the range of function f. So you need to find the range first, and we already got y less than 4 already. If you didn't understand what I said the last part, maybe try wind back and try comprehend it. So we're going to use the domain of x less than or equal 4 to find the range of the g. So we are using x less than or equal 4 here. Okay, so we're going to use x less than or equal 4 to look at the expression of gx and determine what would be the range of that if we use this domain. Okay, so if you sub 4 in the expression g4, it's going to be 5 divided by 2 times 4 minus 9, and that is minus 5, right? Well, g4 is minus 5, but if you think about it, x can be even less than 4. So if you put, say, x 0, right? If x is 0, what will gx be? If x is a negative, like a negative 100, what will gx be? So let's do that. So if I take g of negative 100, that would be 5 over minus 209, right? And that is somewhat a very small negative number. Small as in close to 0. If you ever so decrease the x value, i.e. make it more negative, it will become smaller and smaller. So as x gets smaller and smaller, as x gets smaller and smaller than 4, what happens? Gx gets smaller and smaller and close to 0. Can it reach 0? Not really, right? So if we make x tends to infinity in gx, for example, gx will tend to 5 divided by some large number, 2 times infinity here, some large number, negative infinity. Some large negative number, so that's going to make it tend to 0, right? Because 5 divided by some large negative number, it will tend to 0. So I'm just saying that is the range. So it's going to be what? If you have minus 5 and 0 to be like the two bounds of this gx here, because minus 5 you got it from substituting the actual bound 4 here from the domain that you're using. But then if you think about the tendency of the function, when you make x extreme to one side, in this case negative infinity, it tends to 0. So when you put minus 5 and 0 together, the range of this whole thing should be in between that, right? So I'm just saying that the range of g of f of x at last is going to be in between this. Yeah, so it's just, can it be 0? It cannot be 0, so I don't put an equal sign there. Can it be minus 5? Yes, it can, because we sub x equals 4 in there, so it's just that. So that's my answer there for CII. Yeah? Okay, so for part D. The function h is defined by that, where k is a constant. Find the range of value of k for which the equation fx equals hx. Okay, so we're just going to put fx and hx to equate them. And let's see what happens. So 4 minus 3x squared equals 2x squared minus 6x plus k. Right. But we have the condition where there are no real solutions, right? So this is quadratic function because k is a constant. So if we tidy up everything, on one side we have 5x squared and then minus 6x and then plus k minus 4 on one side, and the other one is 0. Yeah? So no real solution, discriminant has to come. Okay, so discriminant is minus 6 squared minus 4a and c has to be that whole lot, not just k, not just minus 4. Okay, c has to be that. So we have 36 minus 20k and then plus 80, right? Yeah. So we're going to put 116 minus 20k less than 0 because we have no real solutions. And that makes 20k greater than 116. And that makes k greater than 116 over 20, which is simplified to, let's see, if I can use 4, yeah, I think I can use 4. So 4, 2, 4, 9 over 5. Yeah. I think I'm happy with that. So the range of values of k would be that. Is there any limitation to k though? So yeah, k just have to be greater than that. That's fine then. Yeah, I think I'm okay with that. So let's do the next one, number 9. The first 3 terms of a geometric sequence are that, where k is a constant. Part A. Using algebra and making your reasoning clear, prove that k equals 5 over 2. Right. So yeah, we just making your reasoning clear. Okay, so if this is geometric, then we should have r being the same, right? So r is the common ratio. So r is equal to that, and also this, divided by 9, yeah, just this. Yeah, so r being the common ratio here is the same for a consecutive term. I'm just writing the reasoning here just in case it wants that. All right, but then what we do here is we solve this one, right? Solve that equation. So I'm just gonna do, so this is 7 minus 2k to the power of 2 like that, right? Because you cross multiply, so I'm doing cross multiply here, this multiply that, this multiply that. And then we have, so this one, 2 can be multiplied into the bracket, so we get 2k minus 2. So we have 3 to the 2k minus 2. And then when this multiplies that, the powers add up, right? And then we would have plus 4k minus 5 like that. Now, 9 itself is 3 to the power of 2. Yeah? We have 3 to the power of 2 and another power of 2 here, right? So we have 3 to the power of 2 and then 7 minus 2k. And when you power everything there by 2, 2 is going to multiply in front. Yeah, so I get 4 here instead, right? And on the right, and you can see where I'm going here, because I'm trying to make the base on two sides the same so that I can equate the powers. So I have here 28 minus 8k equals 6k minus 7. So I have 14k equals 35, and that is k equals 7572, yeah, as required. There you go. B. Hence find the sum to infinity of the geometric sequence. So sum to infinity is a over 1 minus r, I believe. Yeah. Now we haven't got r yet because we need to substitute. The first term is just 3 to the power of 4k minus 5. So 4k minus 5 here divided by, what is r? R is, well, we need to work that out, don't we? Let me just separate the working. So r is equal to 9 to the power of 7 minus 2 times k is 5. Yeah, I'm just using this one here to find r first. And 3 to the power of 4k. So it's 10, right? 4k is 10. Yeah, 10 minus 5 is 5. So it's 9 to the 2 over 3 to the 5. 9 to the 2 is 3 to the 4 divided by 3 to the 5. So r is 1 over 3. There. Okay. And then we just work out the math there. So this is 3 to the 10 over 3 to the 10 minus 5, 3 to the 5 divided by 2 over 5. Okay, so that's 3 to the 6, 729 divided by 2. Yeah, that's sum to infinity. Or 364.5 there. All right, that would be the answer there for part B. A, verify the x coordinate of A, that is 4. Well, again, verify means that you just inspect back. If x of equal 4 here makes sense, yeah. But if you look at point A is an x-intercept, right? So that means we need to substitute. That means, sorry, if we substitute x being 4 in, we should get y of 0. Okay, A is an x-intercept. So that means if we do y equals 8, substitute 4 in there, 4 to the power of 5 over 2, that's 32 minus 4 to the 1/2 is 2, 2 to the 5 is 32, so that's 0. So yeah, so we get 4, 0 is a valid x-intercept. Yeah, therefore that's right. Okay, so x equals 4. All right, x of A. Okay, B, the line L1 is tangent to the curve at A. Yeah, L1 here at A. All right, and then use calculus to show that the equation of this line L1 is that. All right, so yeah, tangent at A, you know, tangent meaning that the gradient at point A of the curve and the line is the same, right? So we need to differentiate the equation of the curve to find the gradient, basically, because that's what we do. That's what the derivative is for. Okay, dy by dx is 8 for the first term, and for the second term we bring the power down, 5 over 2, and then power minus 1, so that's 3 over 2. Okay, that's dy by dx for the curve. Now at point A, the x value was just found to be 4. So the gradient of the tangent L1, yeah, ML1 here is just 8 minus 5 over 2, substituting 4 in like that. All right, because we know that we need to find the gradient at point A along the curve. Okay, so that works out to be minus 16, right? Wait, hang on, is it? That's 8 minus, so 2 to the 1/2 again is 4 to the 1/2 is 2, 2 to the 3 is 8, 8 divided by 2 is 4, so minus 20 here, minus 12, sorry. Okay, so we just do y minus y1 equals m x minus x1 to find the equation of the tangent. So y minus y1 being the y of A, which is 0, equals m minus 12, x minus x1 being 4. So that's y equals minus 12x plus 48. And that's it. So 12x plus y equals 48 as required. Okay? Part C. Line L2 has equation y equals 8x. The region R shown shaded in figure 3 is bounded by the curve, the line, and the line L2. Alright. Use algebraic integration to find the exact area of R. Alright, okay. So it occurs to me that area R here can be found by subtraction between the triangle and the area under the curve. Okay, so we need to find the area of the R, the triangle, the huge triangle first, and then subtract that, subtract this white area here from that triangle area. All right, so we can find the subtraction, the area we're going to subtract by integrating the curve from 0 to A. Yeah, so we're just going to do 0 to A being 4, integrating this curve right here, dx. All right, just that. Yeah, so that is integrating 8x, we get 4x squared, right? Divide by 2, don't forget. And integrating that, so the power added by 1 becomes 7 over 2. And you divide by that, you get 2 over 7, x to the power of 7 over 2. You just sub the bounds in, 0 and 4. Again, my preference about substituting the bounds into the integration is that I do each term. So, but, well, this one is easy because when you look at the lower bound there, when you sub 0 in, everything goes to 0. So we're just going to sub the upper bound, actually, and just get the value. So that is the area under the curve that we need to subtract from the triangle. Should we keep this as exact value? Yeah, why not? So that's 4 to the power of 3, and then minus 2 over 7 times 4 to the power of 7 over 2. So that's just going to keep exact here, 192 over 7. Yeah? I'm happy with that. Okay. And then we need to find the area of the triangle. Area of triangle. Well, at first we probably need to find the intersection of those two lines up there first, here. We need to find the intersection here because then we will get the height by knowing the intersection here. And when we know the height, we already know the base being 4 here, I think, because x-intercept here is 4. So we do half base height, right? So intersection between the two lines, so we equate them because we have 8x being the line L2 and the other one is minus 12x plus 48 being the line L1 we just found earlier. So this is 20x equals 48. So x equals, divide across by 4, right? So we get 12 over 5. Yeah. And then if you want to calculate the y value, we just substitute x into 8x maybe. One of them will work, yeah? Either. Yeah, both of them should work, sorry. So that is 96 over 5, yeah? And that is the height of the triangle. So we do 1/2 times base, which is 4, also my name actually, times height. What is the height? Oh, yeah, 96 over 5. And then minus 192 over 7. And then that can cancel the 2, so this is, yeah, let's use calculator, you know. So 2 times 96 over 5, and then minus 192 over 7. So we want exact area, so that should come to that. That looks intriguing. Let me check everything here first. So that's 2 times 96 over 5 minus 192 over 7. Okay, so if all that is right, then the answer should be right. But I'm just going to check up here from the integration of the curve. It's just the sense, the cue that I take here that the answer is could be a little, you know, it doesn't look that nice. So I'm taking it the cue here that I should double check everything. Okay, I'm doing it now. Quickly, guys, give me some time. So integrating that, 7 over 2, and then 2 over 7, and then the bounds is 0 to 4. Yeah, that's fine. Yeah, we get the area under the curve there. Subbing 4 in, we should get that. I'm just gonna, yeah, I think I got that fine, right? The 4 to the 3 here, and minus 2 over 7 times 4 to the 3.5. Yeah, same thing. And then we solve the 2 lines intersection there. We get 412, 45, 96 over 4. Yeah, I'm happy with that. Okay, so that's the exact area. Okay, this one, number 11. Figure 4 shows the design of a badge. The shape ABCOA, yep, just the semicircle there, diameter 10. OB is the arc of a circle with center A, okay, and radius R. The region R shown shaded in figure 4 is bounded by the arc AB, yep, and the arc BC. Okay, find the exact area of R. Okay, so I guess I have to draw this out. Okay. This is somewhat actually classic in terms of geometry here. You have an arc in a circle, and then that forms like this kind of shape right here. Classic shape, yeah. We want to find R. Give the answer in A root 3 plus B pi. All right. So the radius of circle center O here is 5. Okay, and the radius of the circle with center A is also 5. Yeah. So I'm saying that this is also another circle with center 5. Sorry, radius being 5 here. It's basically identical circles on top of each other like that, but then they are both passing the centers of each other like that, right? If you think about it. But this is just partial, yeah, from the other circle. So we probably need to draw a line. So whenever you see this, maybe draw some line here like that. And we might want to find this area here first. Okay, how do we do that? Well, that can be done by, well, if we draw another line here, you can see that this would be called a segment minus segment area. Yeah, so if I draw just a separate piece of pizza here, and then we have also a triangle here and a sector there. So the segment area here, the little segment area here, is found by the area of the segment minus the area of the triangle, right? Make sense? And that is, if we know this to be theta, yeah, so that should be 1/2 the area of the segment being theta r squared. That is the formula there. And theta is in radian, right? Minus the area of the triangle, which is 1/2 AB. Yeah, this is using a formula where you know A and B and theta, but A, B are just radii. So they are the same, they are r. So this is A times B being r squared, and then sine theta, right? So that's actually the formula of the segment, the little segment in the sector like that. Yeah? So we can find the segment using this formula right here. I'm just gonna, yeah, I can keep that. And after you found that segment, you will be able to find this whole thing. And then subtract that from the semicircle area, right? Okay? So let's do that, right? And we know that, yeah, this is the tricky part. We need to know this angle, right? Or this angle. Well, let's do this angle. Sorry, this angle here. It doesn't really matter, does it? Because this is also 5 centimeters, because it's the radius of the left circle here. Isn't this also 5? This is 5. This is 5. Oh, this is a equilateral triangle. So we know that the angle inside is 60, isn't it? Right? Yeah? So that means we can calculate the segment area by area of segment is 1/2 theta. Theta is pi over 3, yeah? Times r being 5 squared minus 1/2 r 5 squared. Sine pi over 3 is sine 60. Sine 60 happens to be √3/2. Okay, so if you simplify that, that should be the area of the segment. Let's see. Okay, so this is 25 over 6 pi minus 25 over 4√3, right? Okay. And let me just shrink down a bit here. All right. So we get the segment area there, but in order to find r, we need to subtract the triangle and 2 segments. These 2 segments should be the same, right? It's like looking from another angle, just still get the same shape. So r is the whole semicircle area, which is pi times 5 squared. So 25. I'm just going to do 5 squared pi, yeah? Divided by 2. Don't forget, because that's a semicircle, it's half the circle. And then minus. Okay, we have 2 of the segments. We gotta subtract 2 segments there. And 1 of the triangle. Yeah, it's still the same triangle. So it's 1/2 5 squared is this guy right here, basically. Okay, so I can just write 25√3/2, right? Yeah? Wait, hang on. Oh, 4, sorry. That's why it's weird, because I had a formula in mind and it tells me that it's something else. Yeah, sorry, I didn't multiply 2 and 2 there. Okay, now we just simplify everything and make sure that it's in the right form as required there. Okay, so what do I do with all of them? So 25 over 2. I'm just going to gather all the pi terms there. This is minus 50 over 6. Is there anything else? No, that's it for the pi. And then I have a plus here, 25 over 4√3, and minus, that cancel, huh? Right? So, yeah. So we have, wait, what? Not cancel. Shouldn't cancel because we gotta have √3 in there, in the picture. What did I do wrong? Oh! Stupid, I forgot to multiply 2 out. Yeah, so this is plus 50 over 4 root 3 minus 25 over 4 root 3. Yep. I mean, I did multiply for the pi term, but not for the other one. Forgot to expand that in. So this is, what is it? So this is basically 75 over 6, right? If I multiply 3 and 3, so 75 over 6, that's 25 over 6 still. Yep. Pi, what is that then? That's 50 root 3 minus 25 root 3, so that's 25 root 3 over 4. How do we make it in that form? Well, we have the root 3, we have the b, that's done. Because a and b are rational numbers, meaning that they can be fractions. Yeah, and that's done. Okay, next question, number 12. Harmonic function, i.e. the thing you see right here, asking to express that in the form of that. This is a harmonic function. It's just a single trig function from a mix of multiple functions from this. Yeah. Okay. So express 140 cos theta minus 480 sine theta in the form of that. Okay, the way I do this is just finding k first. Normally it would be in r, but okay, they use k. Never mind. So we do k equals the square root of the constant terms in front of cos and sine there. So this is 140 squared plus 480 squared straight away. Yeah? And if we do that, we should get an exact number. Yeah. Oh, it's 500. Okay, easy. Okay, so k is 500 basically. And well, the way I go with this is I don't memorize. The way I do this is just expand. So k cos theta cos alpha minus k sine theta sine alpha. What I just did was expand using the additional formula for cos a plus b there. Yeah? And we can see that 140 cos theta must be the same as k, which is 500, cos theta cos alpha. Well, the cos theta cut out like that. That means alpha would be arc cos of 140 over 500. Solving that equation right there. I didn't use any formula here. I mean, yeah, you can, but I mean, at least I have to know that the k is the square root of those two numbers, squares of those two numbers. Well, that one can also be proved, actually. It's not that hard, you know. It's like you do the same thing here. You equate these two, and then when you do the square root of those two numbers squared, okay? All right, so I'm just going to do arc cos here. Sorry about that. We need to do alpha in degrees. So I'm just changing that to degrees. And then arc cos 140 divided by 500. That gives me 73.3739795 blah blah blah. Rounding that to 2 decimal places, so it's that. Yeah. Okay, so that's my alpha there. So this is so equals 500 cos theta plus 73.74. That's my answer there. Okay. A scientist studies the number of rabbits and the number of foxes in a wood for 1 year. The number of rabbits R is modeled by the equation. R equals A, blah, blah, blah. And now if you notice, it is just mimicking the earlier trig form here, but just changing theta to 30t. You can notice that, right? So if we were to change relevant part here to a harmonic form, we gotta not look at A for the time being. So I'm just saying that the R function here is just A plus, yeah. If we change just the relevant part there to a harmonic form, it would have been 500, yeah. And cos, hang on, cos of theta, which is actually 30t, yeah. Just compare the form there. And plus the alpha, which is still the same as 73.34, right? That's just the substituted harmonic form. Okay, given that during the year the maximum number of rabbits in the wood is 1500, find the complete equation for this model. All right, we have found that equation there. So the maximum is 1500, the maximum. So the maximum happens, and this is very key to doing this question. The maximum happens when this whole thing goes to 1, right? You got to look at this. If this sign is negative, then you would have had to substitute this as -1. But if this sign is positive, then of course, maximum is, we have to make it as great as possible. To do that, this has to be 1 because it cannot go greater than 1, that whole function there. So R max is just A plus 500, right? Well, that means we equate the 1500 that they told us to this. And we get A equals 1000. Answer. Okay? That's it. For II. Hence, write down the minimum number of rabbits in the wood during the year according to the model. The minimum number. Well, if maximum number is 1500, and we already know that A is 1000, so minimum number, R min, would be 1000, which is the A there, minus 500, right? Because now we want minimum. So the cos function there should go to -1. So it's 500. Yeah? Okay, so B is done. Next is C. Use the information to comment on the model for the number of rabbits. Well, if you progress the time for as long as possible, let's say, it seems like the quantity of rabbits fluctuate. Somewhat that is not quite realistic, is it? Because, I mean, if everything goes right for the rabbits, for the whole group of rabbit there, they should maybe keep increasing, maybe, or not fluctuate this much. I mean, depending on the biology, the ecosystem of the rabbits there, which I am no expert on that, this is a lot of fluctuation, and the number of rabbits have something called bounds. Like they cannot go greater than 1000. Why not? Cannot go lower than 500. Why not? Right? It's just maximum, minimum here seem to be an unrealistic limitation to the number of rabbits. Okay, so wait, which one are we doing? Okay, the actual number of rabbits in the wood is at its maximum value in middle of April. Sorry, I forgot to read that. Okay, so in the middle of April, it's kind of like Easter, right? Closing into summer. Ooh, hang on. Okay. I think we need to check something here for the foxes as well. Wait, T is, what is T again? T is months. T months is the time after the start of the year. So in this case, T is about the end of April would be 4, right? T is about 4. Okay, sorry. We need to substitute 4 in. So if T equals 4, then R equals, what is A again? 1000 plus 500 cos 120 plus 73.74 there. I'm just going to try calculate this value first. Yeah, I didn't see that it says degrees. Well, oh, sorry. This has to be 120 plus, right? Yeah, 4 times that is, yeah. Okay. 120 plus 73.74, and that is the value. So that's about 514 rabbits. Well, let's have a comment on this. In April, and the number of rabbits is nearly minimum. Let me see. Oh, this is okay. Yeah, I don't know what I was thinking. Okay, it says the actual number of rabbits in the wood is at its minimum. Yeah, at its minimum in the middle of April, and in the middle of April. Well, hang on, middle of April, I should have substituted 3.5 in, shouldn't I? Yeah, I should have substituted 3.5 in, because in the middle it should be halfway in the middle of the month 4 here. So okay, gonna try do that again. Okay, so I'm just gonna do that again. Sorry about that. Okay, we get about 500, right? 541.2. Okay, so that is pretty accurate. Yeah, so that's nearly 500, which is actually the minimum. Okay, so which is about 500, which is the minimum of the function r. So the model that we use, the model that we substitute to get the minimum, is actually giving you the minimum when you substitute 3.5 in. So the function gives the minimum indeed, because the actual number is also minimum. So the model is accurate because it also gives the minimum, right? So it should be accurate. So that's the working there. Now the number of foxes who probably eat rabbits in the wood during the same years modeled by that equation. The number of foxes is at its maximum value after t months. Okay, find according to the model the number of rabbits in the wood at time t months. Okay. After t months, right? The maximum, the minimum. Okay, let's find the minimum foxes first. The minimum fox occurs when the sine function goes to -1, right? So that's 100 minus 70, which is 30. And that happens when sine 30, we put a t here, t months, plus 70 equals -1, right? So to make it -1, the t value here, the first t value, so 30t plus 70, the first value to get -1 would be 270, right? So if you plug in the equation, the calculator, sine 270 is -1. So that means t here is 340 divided by 30. That's about 11.33 months. Okay, so that's about almost the end of year. The number of foxes is at its minimum value after t months. finding, according to the models, the number of rabbits in the wood at time t months. So we're just going to use that value t there to substitute in the previous model. So rabbit at t equals that. So I'm just going to simplify as 34 over 3 here. Yeah. Equals. Using the previous function we obtained, which is 1,000 plus 500 cos of 30 times that plus 73.74. Okay, degrees. Yeah, I shouldn't write that, it might be to the power of 0. Just leave it at that. Okay, so that's everything. Yep, I think I'm happy with that because we got t. Let me double check the capital T value again. Oh no, I made a, yeah, you see, if you don't check, you don't see. I made a mistake. It's 270 minus 70, so that's 200 over 30, which is 20 over 30, 20 over 3, right? Yeah, it's a bit dark right now in here. That means a little late now. If I have any excuse for that. Okay, so I'm gonna have to substitute the right value here. There you go. So this is 1,000 plus 500 times cos of what angle there? It's 273.74. I think I'm okay with that. 1,000 plus 500 times cos of 273.74, right? Ooh. Yeah. So that is equal to, what was it again? 1,032.6. The number of rabbits. So I'm just going to say that then. Is that too much? Is that far from the... Yeah, the maximum is 1,500, so that's fine. We're fine. Okay, I'm just going to call it at that. And the next question, number 13 now. Probably the last one is 14, I think. A, given that A is a positive constant, use substitution x equal that to show that that. Okay, so we just use substitution in integration here, right? Okay, so dx by d theta, yeah, equals, we are just going to differentiate that first. A is a constant, so that's fine. So differentiating sine squared, I get 2a sine theta. And then chain rule for the sine again, I get differentiate sine, I get a cos, right? So you bring the power down, power minus 1, and then you chain rule the sine theta again. You get a cos theta. That is a chain rule. If you are not familiar with the chain rule yet, or you need some more practice, just go check that video right there. And then what do we have here? Okay, so we need to substitute the dx. So dx is basically 2a. Yeah, I think we can, hang on. Should we do that yet? No, maybe not. Okay, I'm going to keep everything like this. Maybe it will cancel later on. So integral of 0 to a. Here. Okay, let's do the bounds as well. So, so if x equals a, then theta equals pi over 2. Yeah, because you can cancel a and then you can find theta to be pi over 2 because that gives you sine theta of 1. and then if you put x equals 0, obviously theta would also be 0. So I'm just finding the bounds here first, right? So that means this whole thing will be equal to that. Well, no, I need to do step by step. So this is 0 and pi over 2. And then x to the power of a half would be a to the half. Yeah, I'm just, using this expression here to put it to square root. So this is just sine theta. Okay, a to the power of a half and sine theta. Move it to the left a bit. And then multiply by square root a minus x. So that's just a minus a sine squared theta. And then dx would just be that whole thing there, which I run out of space here. I need to move down a little, maybe here. Okay, and then we're going to bring the whole thing down here. That's it. Okay, so let's simplify the thing, right? Let's see what we have. Okay, so the whole integral there, we have a to the power of half. This one right here, right? I can take square root a out, yeah? Because look, inside there is just a and 1 minus sine squared theta, right? In the square root. So if you take the a out from the term there, you get a to the half. Because I want to group that to multiply a half and a half, you get a, yeah? And then you have a sine theta here. Square root of this guy then, which is a cos squared, isn't it? Because this is a trig identity. That's a cos squared. So square root of that is just cos theta. And then you have another 2a here. Then I can group them there. And maybe I'll put another a here. And then sine theta cos theta again. Or actually, I can just do sine squared and cos squared already, just to save some space in writing. Okay? So because we know the sine 2 theta is 2 sine theta cos theta here, right? Let me just move that a little to the right. Well, that means if you want to square this, then you get everything squared. So that would be 4, that would be squared, like that. Okay? So this is saying that to get that, then you need 4 of the sine squared and cos squared, right? So that means, okay, so this whole group thing would be a squared. So I have a squared here in front. And then that whole thing inside here will be 1/2 sine squared 2 theta, right? If you rearrange. So basically, if you look at this, then that would be that. So that's sine squared 2 theta divided by 4. If you sub this into just this part, 4 will cancel with 2. That's why I get a half here. Just algebra there. Yeah, and that's as required, I think. So yeah, so yeah, we can just wrap up just writing what they want there. And this is sine squared 2 theta d theta. And then of course we need to probably do something with it. B, hence use algebraic integration to show that that is equal to k pi a squared. Alright, so we need to integrate that. Now, again, you need to make use of the double angle formula. Because we know that if cos 2x is 1 minus 2 sine squared x, then you can put x to anything. Yeah? I mean, you can put x to anything. So in this case, if x is 2 theta there, right? So this would have been 4 theta. just like that. You can double both sides to any combination, but one has to be half of the other, right? So that means sine squared 2 theta as a subject is then 1 minus cos 4 theta divided by 2, right? So I'm just substituting that. 1/2 a squared from pi 0 to pi over 2. Is that the right expression there? Yeah, the whole thing, just the whole thing. Okay, yeah, just 1 minus. So I'm just going to split into 1 over 2 minus cos 4 theta over 2. And then that is d theta, right? Yep, 0 to pi. I'm happy with that. So let's go on and integrate that, right? So 1/2 a squared here remain the same. We have the bounds. We have in the integral here, it's going to be theta over 2 because we are integrating with theta there. Integrating cos, we get sine. So that is sine 4 theta. And then we do the reverse chain, dividing by the derivative of the angle there. So it's divided by 4. So this becomes 8. And the bound 0 to pi over 2 just subs in. Yeah. All right. So what is that? Is 1/2 a squared. And then I would like to do it this way. Well, it's just pi over 2 for that. And then sub 0. Okay, in this case, you substitute 0 in, everything goes away. Right? So you just have sine of 2 pi there divided by 8. Well, sine of 2 pi is 0, isn't it? Right? So it's just pi over 4 a squared. Yeah, or 1 over 4 pi a squared. K is a constant to be found. So I think I'm happy with that. Next question, and perhaps the last one. Ooh, long one here. Number 14. A balloon is being inflated in a simple model. The balloon is modeled as a sphere. The rate of increase of the radius of the balloon is inversely proportional to the square root of the radius of the balloon. At time t seconds, the radius of the balloon is rcm. Write down the differential equation to model this situation. So it says the rate of increase of the radius, that's dr by dt, yeah, it's an increase, so it's a positive. So equals inversely proportional. So k divided by the square root of radius. So that's it. Yeah, nothing else, because it's a positive, so we're just going to put k there, and k being a positive number. All right. So k is a positive number, like that. Yeah. Okay. And then b. At the instant when t equals 10, the radius is 16. The radius is increasing at the rate of that. Solve the differential equation to show that. Okay. So we have two conditions here at time equals 10. We got to be careful. All right. We'll make use of that later. Okay. So at first, we need to separate the variables first. So differential equation, there are two questions for this topic now because we did it the other question. So we do root r dr equals k dt. Just separate the variables, right? Let me just check again. Inversely proportional. Yeah, I'm happy with that. Okay, so we are integrating both sides. This is r to the power of half dr, and that is just k dt. So that becomes r to the 3 over 2 times 2 over 3, right? That is just power rule there. Equals kt plus c. I'm just going to make it like that. Okay. Now at t equals 10, yeah, substitute the conditions now. Radius is 16. So we have radius is 16. So 16 to the power of 3 over 2 equals 10k here plus c. We haven't got anything yet. All right, but then we got an equation between k and c, so let's see what we get next. 16 to the power of 1/2 is 4. 4 to the power of 3. Let me use a calculator just to be safe. Times 16 to the power of 3 over 2. So that is 128. Oops. 128 divided by 3 equals 10k plus c. Just going to keep this equation for the time being, right? Because I think we need more information. The radius is increasing at the rate of 0.9. So it's just this equation here. If we talk about the rate, it's the derivative function there. So the rate being dr by dt is 0.9. Yeah, when the radius is at 16. So we put 16 here. So that makes us being able to find the k value straightforwardly. Okay, so k is just 16 times 0.9 there, 72 over 5, right? Is it? Yeah. That's the value of k. And then since we know k, we can find c, right? So therefore c is equal to 128 over 3 minus 10k, which is 10 times 72 over 5. And that is equal to 128 over 3 minus, that's just 72 times 2, right? If you do the math there. Ooh, that's minus 304 over 3. Interesting. Okay. That is the value of c. So we need to show. Okay. So we got c, we got k. So it's then 2 over 3 r to the power of 3 halves equals k, 72 over 5 t plus c there. Okay. Yeah, I'm just checking. Okay, so how are we going to simplify this? Well, something tells me that if we multiply every side by 2 over 3, we're going to get there. Let's do that. So we get r to the 3 over 2 as a subject. Yeah. And then 2 over 3. So 3 will cancel 72. 3 times 72 divided by 3, we get 24. So 24 times 2 is 48, right? Yeah. Yeah. And then, times 2 over 3, you kidding me? Ooh, it looks like it should be simplifiable there. Hang on. I think I did something wrong here, guys. Let me just double check everything. Oh no, I should multiply 3 over 2. Oh, I'm stupid here. Okay, let me do that again. So multiply 3 over 2, we get 36. 36 times 3 is 108. 108 over 5 minus, 3 cut, so this is 15 too. Ooh, and that's horrible because I don't get 10 there. Did I get the other one? No. Everything is wrong here. Hang on. Something must be wrong. Let me check the integral again. Square root of the radius. Yeah, I think I'm okay with that. kt plus c. When t equals 10, I sub 10 in. Radius is 16. 4 to the 3 is 64. Okay, and then dr by dt is 0.9. When the I forgot to square root this. Okay, yeah. So k is 3.6 or Or should we make it 18 over 5, right? Yeah. Sorry about this. And then this is, yeah, 18 over 5. So what is that then? That's 36 instead, sorry. 20 over 3. All right, so should be hopeful. And is k still? No, k is changed now. 18 over 5, right? Okay, so we're still multiplying by 3 over 2 there. So we get 927 over 5 t, yeah, and then 10 here. And 27 over 5 is basically 5.4, indeed. As required. All right, took me a while to figure out where my mistake was. Hence, find the radius of the balloon when t equals 10. Okay, that's just subbing that in. Okay, you know what? Let me just make r the subject. So it would be the whole thing to the power of 2 over 3. Like that, right? Nearest millimeters. All right, that's fine. So 5.4 times 20 minus 10, and then to the power of 2 over 3. 21.256, blah, blah, blah. So that's 21 millimeters. Because r is in centimeters. Don't get tricked by that. Okay. I just check. So I know that that would have been wrong. So it's that centimeters, right? So it's that millimeters instead. Yeah, almost got tricked there. Okay, nearest millimeter. Cool. D suggests a limitation of the model. Okay, limitation again. So as you can see, guys, if t tends to infinity, r keeps increasing forever. And the rate, let's talk about the rate. Oh, okay. So the rate seems to be inversely proportional to the radius. So if the balloon gets bigger, the rate is smaller and smaller. Okay, balloon gets bigger, the rate is smaller and smaller. Okay, that's kind of realistic. But this is telling you that the balloon gets bigger and bigger forever, right? Probably that is something that is not quite true. And if you put t equals 0, the radius starts at 10, right? Okay. I'm gonna go with there is no upper limit of the radius, which isn't the actual behavior of the balloon, because I mean, balloon should burst somehow at some point, right? If you keep increasing the size. So there is no upper limit of the size of the balloon, which is unrealistic, right? There is no upper limit to the size of the balloon. Unrealistic. Yeah, I'm going to go with that. Is there any more question actually? Well, yes, actually, there's number 15 here. Okay, so 15, I show that k squared minus 4k plus 5 is positive for all real values of k. Okay, so we're just going to use discriminant here to prove, right? No, not discriminant, I mean complete square. So k squared minus 4k plus 4 plus 1, yeah, equals 2 squared plus 1. Right? So that is a complete square form. And since k minus 2 squared greater than or equals 0, so k minus 2 squared plus 1 is greater than 0. And therefore, this is true, well, for all real values of k. Yep. Okay, so that's part I. Part II. Almost didn't do this question. The student was asked to prove by contradiction that there are no positive integers x and y such that blah blah blah. The start of the student's proof is shown below. Show the calculation and statements needed to complete the proof. Right. So there are two positive integers x and y, and they have the expression on each brackets, and they multiply to 28. Okay, so if x and y are integers, then 3x plus 2y and 2x minus 5y should also be integers. Yeah, so here we are gonna conclude that this and 2x minus 5y should both be integers, right? Because we know that x and y are integers, right? Yeah. Now we assume that there are positive x and y. There exist positive integers x and y such that in the brackets they multiply to 28. And they start by first letting the first brackets being 14 and the second being 2, right? And then they prove that at the end x and y are not integers, so that contradicts. But we need to exhaust the case here because it's not just 14 and 2, it might be something else. Now, in this case, right, if we're going to go for all the cases where you got two values multiplying to get 28, it's going to be too many because we have 1 and 14, minus 1 minus 14, you know, and 2 and, sorry, 1 and 28, minus 1 minus 28. So we got to think of it here, right? Look, if x and y are positive integers, that means the first brackets should be greater than 0 because x and y are positive integers. Think about it, right? How can you get negative integers? How can you get 3x plus 2y being negative if x and y are positive? Not possible. So if the first brackets will give you a positive integer, then the second bracket should also be positive. Now the only case where the only remaining case where both brackets are positive would be, so 3x, we need to complete the proof, so we need to, okay, so if 3x plus 2y equals, so let's make it, and it seems like 3x plus 2y should be greater than 2x minus 5y, right? If you think about it, because 5y is like, I mean, it's like you have a 3x plus 2y and the other one is 2x minus, so the minus one should be smaller. So I'm just going to say also, and 3x plus 2y greater than, yeah, that's the logic there, 2x minus 5y. Okay, I'm just going to go to the next page here. So if 3x plus 2y, so we're gonna make it 4, right? And 2x minus 5y. So if this is 4, the other one should be 7, but hang on, we just let this be 7 because it gotta be greater than the other one. So this one is 7, the other one is 4. Okay, and also 28 and 1, don't forget. So maybe I'll do 28 and 1 first, and yeah. So we solve simultaneously, right? How do we do that? Well, I'm just gonna multiply this by 2, so I get 6x plus 4y equals 56, and multiply the bottom one by 3, so 6x minus by 3, 15y equals 3, yeah? And then I subtract them, yeah? So this is 19y equals 53, so y is 53 over 19, and x is something, not a whole number, of course. 1 plus 5 y divided by 2. So what is that? 1 plus 5 times 53 over 19 divided by 2. Yeah. Not integers. We just copy that. And then the next one, the first case there, if another case, 3x plus 2y equals 7. Yeah, 7 isn't done yet. They just did 14 and 2. And 2x minus 5y equals 4, right? Again, we're just gonna do 6x plus 4y equals multiplying by 2, right? Yeah, 14, and 6x minus 15y equals multiplying by 3, we get 12 here. If we subtract them, we get 19y equals 2, so y equals 2 over 19, and x is 1 plus 5y over 2, right? Oh, no. Gotta substitute again. So 4 plus 5y over 2 instead. Okay, so 4 plus 5y being 2 over 19. Yep. That's it. So not integers either. And statements needed to complete the proof. So x and y are not integers in any case. Therefore, contradicts the assumption that they are integers. Therefore, yeah, there are no positive integers x and y such that, I'm just going to write the whole thing, right guys, so you know what I'm doing here. I mean, I'll probably mark this okay later on. Yep. Okay, here we go. So let's mark the paper, right? Okay. Okay, here's the mark scheme for the paper we just did. So let's go from the beginning. Okay. Number 1, k equals 12, fine. Number 2, check all the term. Yes. And minus 2 over 9 is outside the range. Okay. Number 3, minus that. Change of sign and function is continuous in the interval, so there is a root. Got that. Down here, 3.672. This is 1 plus. Okay, yeah, nailed it. Number 4, yeah, first principle, so I got all the parts there. Number 5, minus 2 plus 6x, yeah, that and that, okay. Number 6, 2 and 5, yep. 7 over 7, 17 over 7, and then part 4. Ooh, okay, I got part 4 wrong here. Sorry, part C. Maximum is 3. I forgot the minimum. Wait. Yeah, greater than 1 over 2, but why can it not be greater than 3? Okay. So, wait, okay. Yeah, that's the pitfall there. I forgot to check where the line is, like, when the line is parallel to this. Yeah, you have another case here. Totally forgot about that. So in this case, if you equate, hang on. So the line should be here. Yeah. So if you found the gradient should be the same as this, right? So because we already know that the V shape has a 3x part in the modulus, so the maximum gradient here should be less than 3. If it's 3, then it's not going to cut another point, so it should be less than 3. That's why I got it wrong here. So minus 1, I think. Yeah. Okay. I lost 1 mark here. Oops. Okay, so H there. It's fine. 3 hours and 28 minutes, I think. That's fine. Yeah. And then 0.9, yeah. Ooh, hang on. If I forgot the units, will I get the marks? Let's see. Correct height, including units. Oh no. I need to give the units. Yeah, I didn't see that coming there. Didn't see that coming at all. So minus 1. Yeah, because some questions ask for, yeah. I mean, actually, let's look at the question, right? See if it's actually want the unit or something. Wait. Is this question 7? Okay. No, it doesn't want any units. And H is already in meters. But it asks for the height. It doesn't ask for the value of H. So if it does ask for the value of H, then only by answering 0.9 you would have got the mark. I would have got the mark here. But it asks for the height, right? If it doesn't refer to the actual variable, then you should give the units. This is just like physics, actually. You never forget units. All right. Should have known. Anyway. Yeah. Okay, number 8. Okay, that's fine. G inverse, not 0 here. C part I. Yep, nailed it, I think. This is, yeah. ci, yeah, part D, that is 5.8, right? Yeah. Okay. Number 9, 5/2. That's right. Number 10. Huh? Yeah, substitute equals 0. Yeah, sure. That is as required. Part C. That is right, I think. Yeah. 11. Yeah, looking at the final line there, I got the marks. 12. 500, blah, blah, blah. BI, got the equation, so, yep. What does it ask? Doesn't it ask for the maximum and minimum? Minimum is 500. Maximum is 1,000. All right, yeah. Wait, does it actually ask for minimum? Why does it write an equation like that? I'm just checking the question. So 12 part BI says find a whoa! BI says find a complete equation, and I gave it the maximum. Right. Okay. Is there anything that can be implied here? But I wrote this, right? I wrote this, and then I say A equals 1,000. So let's see. BI. Correct equation for the model in either form including R equal following through in their numerical K. Allow for that R without the brackets is correct. Allow mark if they truncate or round it otherwise. Yeah, you know, I think I got it. Right, guys? I think I got it. Because I actually, at least I did the 30T there and just found found A to be 1,000. It just didn't say it at the last line, but you know what? I'm not going to give myself a mark here, so just -1. You know, just being very fair here, or too harsh, maybe. But the second mark here, definitely. And part C, R is about 500, so reliable. Yeah, accurate, same word, I think. It's 1,033, so that's fine. 13A. A sine squared. Yeah, everything is fine, right? Part B, let's see. What? 1/8? Mistake again, isn't it? Let's see. I got this fine, so I got up to that, right? And then what went wrong? Huh? Pi/2. What? Don't you have to just substitute the bounds in? And the bounds being 0 to pi/2. Interesting. I'm not sure if I get this mark right here. So A1 here, let's see. B, correct integration. Here mu may be 1, condone lack of limits. 1/2. Integrate cos, we get a sine. What? Okay, let's check the integration again. That is right? Huh. I'm not seeing what went wrong. Okay. Okay, what? This is weird. Okay, let me check the question, yeah? So this is number 13, right? Yeah, I think so. Nope. Yeah, 13. Hang on. 0 to pi. I'm wondering why is there an a squared over 4 there, because that is what I got different from the mark scheme here, right? I'm just looking at it and trying to fathom it here. Right, okay. I don't see it yet. Oh, right. Oh no. Substituting pi over 2 in here, I should get pi over 4. Right. So this should be pi over 4. Yeah, alright. Yep. Yeah, but I think I got this mark right here. Yeah, because it's just, I think it's just, yeah, let's see that mark. Apply limit to the correct integral and proceeds to this. Wait, correct integration? Yeah. So yeah, after I got up to this, then it's fine. So I minus 1 down here. Silly mistake this is. This is silly mistake. A silly mistake indeed. Okay, number 14. Got that. And then, yeah, almost flopped for this one. Almost. Yeah, got it. Showed it. And then 24. What? Got a different R here. You gotta be. Oh no, hang on. Oh no. No. Oh my god. This is a plus C. Oh my god, this is catastrophic. This is a plus. Oh no, this is unacceptable. So I have a minus 1 here. This silly mistake is unacceptable by me. Okay. So I got a method mark here, but the final accuracy is not right. Okay. Yeah, there is no upper bound limit to the size of the balloon. Unrealistic. Yeah, balloon may burst. Yeah, I mentioned that, but let's see if what I wrote here is kind of like fine. Wait, what? There is a question 15. Model will not hold indefinitely when there is unlikely spherical. Model predicts balloon will increase size without limits. Yeah. Okay, I got that, right? Okay, so number 15. Okay, here we go. 15. Yeah, completing square, that's fine. It's always positive, that's fine. Part II, it's just the proof there. Okay, so attempt solve for one pair. I have 28 and 1 here. Yep. Attempts to pair. What else? 28, 1, 7, and 4. I got 2 of them. Yes. Wait, attempt to solve all 5 pairs? Wait, hang on. There are 5 pairs? Really? Are you serious? 5 pairs. Or e.g. this and this. Oh, right. So I think I got them, right? All other cases are not possible as, yeah. Oh, yeah. I think I did that. Okay. I think I did say that other cases are not possible because of that. Yeah. So I say that has to be greater than 0 and that has to be greater than that. I think that's the same thing. Yeah. Okay, so I think that's fine. So I got 1, 2, 3, 4, 5, 6. 6 marks deducted only from my stupidity, silly mistake, silliness, whatever you call it. So okay, so feedback, guys. I think, yeah, first one is fine, second one is fine, right? This one, yeah, you got to be careful with this. It's the validity thing. You need to understand the concept. I already explained that. Number 3, well, it's just Newton-Raphson, so that's fine. Use a formula. Number 4, nothing too specifically. Well, you just have to know that the decreasing function means the derivative is less than 0. Number 6, yeah, this one got me. I forgot to check the. Normally I would, but I don't know why this time I didn't. Yeah, the parallel gradient to that, right? So can't miss that. So that's the upper bound of the gradient. Yeah. Okay. Make sure you understand that one as well. This one, let's have a look. This one is number 7. Okay. Yeah, this one was fine, right? Oh yeah, the units. Well, normally math papers don't do this, but yeah. Well, the only reason I see why they do that is because the word height doesn't imply the units. So if they say h rather than height here, maybe I would have got the mark. Yeah, but that's probably the reason why they do this to us, or maybe to the people last year, right? Not us. Yeah, that's number 7. Number 8 here. Yeah, try make sure you understand what I walk through and explain about how you find the range of the composite function. All right, guys. Wait, where's that? The range of the this guy right here, right? That's very important because basically it's just whatever is inside, you have to find what it is. So that's why the range of fx will be the domain you use to consider the gx, right? But if the other way is to look at the g of fx here, so this is the function g of fx. Where is it? Yeah, so this function here is g of fx, right? Well, Can we use this one? Yeah, so if you plug in x of anything in there, yeah, like if you look at the fraction, the function here, yeah, x squared is greater or equal to 0. If we look at the bounds there, if the bottom part is minimum at 1, so -5 is one bound. You already got it from there. But then if you think about the tendency of x squared there, if x keeps increasing, the bottom part will be a very large number, and that makes the whole thing 0, right? So 0 is the other bound. So you can look it from there as well, right? So that's fine. Okay. This one, number 9, yeah, everything is fine. So you just have to bear in mind that the common ratio is the common ratio. So it's the ratio between two consecutive terms, right? The next one divided by the current one, okay? And yeah, number 10, yeah, this one fine. I mean, you probably have your own way of finding the area, but I would like to, do the triangle here. I mean, you can do two triangles, that's also fine, but if you can't see that this is the whole triangle, then you would need to do split, right? Two triangles added up. And then question 11, yeah, this one is fine. It's quite classic, just the areas of the segment there, and then you make use of it later. Number 12, 12 is fine. Yeah, I was stupid on this one. I didn't read the question. They want a complete equation. I thought they want A or something. Somehow I didn't read the question and thought that they wanted A, but they didn't. They just wanted the complete equation, and I was asked to myself there. And C, yeah, C was fine there. Okay, 13. I lost more marks towards the end because it's now about midnight. Yeah. The state of mind is probably a little shaky when it's darker and darker. Wait, what? Yeah, I lost mark in the integration here. Yeah, because I subbed the wrong bounds in. So I did sub pi over 2, but somehow I subbed the whole pi over 2 into the theta over 2. It's actually pi over 4 there, right? Should have been pi over 4 there, obviously. So yeah, you gotta go through the integration bit here very carefully. It's very easy to make mistake along the way when you have a lot of numbers and a lot of parts. And this part here, yeah, a lot of algebra there, a lot of terms to simplify. Hopefully, yeah, you will be all right with that. 14 here, the rabbit thing, yeah, got the most of me here. I mean, got the most marks from me. I lost marks the most here in this question, I think. 2. Well, still fine, right? First, I lost it because there was a plus C, and then when I got C to be positive, and then somehow I wrote negative here, right? A bit careless there. And then that is a follow-through mark. I lost another one here because I got a wrong equation, but because I follow through here, so I got the method mark there. And there's no upper limit here is correct answer for the rabbit. Yeah. Okay. Wait, this is the balloon, not rabbit. Sorry, this is about balloon. All right. Okay. It's really dark, right? Maybe a bad idea to walk through at night. Okay, 15. Yeah, everything is fine here, 15. And that was it, guys. For 15 here, I think, yeah, you need to exhaust all the cases. But logically, I didn't because it was too many. What I did here instead was just use some logic about numbers to, conclude that there are just only 2 cases because the first brackets will always be greater than the second brackets, right? No matter what x and y are. Okay, so I think that makes sense to prove just two cases, right? So yeah, that was it. So I hope that was all useful, and I'll see you in the next one. Bye.